Okay, you have to start a little bit in electrostatics, so my apologies to Logan and to Jarrett, because for you this will be a preview, not a review. Okay, so we've finished up vectors with the exception of your beautiful little quiz, which will now be tomorrow. And before we can get into magnetism, we need to look at electricity and electrostatics because magnetism is very closely linked with it. And so the better you understand electrostatics and electricity, the easier magnetism will be. Now, Jared and Logan, the good news is most of the other people in the room with you did not like electrostatics all that much. And so they're groaning right now saying, I need to understand it. So this review and this preview are both important no matter whether you've seen it before or not. Now, for it to make sense, we're going to go back to Newton's universal law of gravitation that Jarrett and Logan, you would have seen in grade 11 physics with me because I used it to develop that Fg was equal to mg. If you remember when we talked about it in grade 11, we said, okay, these two m's are the masses of the two objects, m's, masses of the two objects between which the force exists. Be good if I wasn't off the screen, eh? Objects. The r is the distance from the center of one to the center of the other. And the g was a universal constant, universal gravitational constant. Sorry, not lined up in the right spot. There we go. Universal gravitational constant. And that resulted in Fg, which is the gravitational force of attraction, between any and every two objects in the universe that have mass. So the main point of it was as long as any two objects that have mass will put a gravitational force of attraction on each other. And in grade 11 physics and in grade 12 physics both, we actually figured this out. We use it and we plug in the numbers and we find out what Fg is for two people in the room. Okay, and we discover it's really tiny because their masses aren't very big. But if we trade in one for the Earth, then it gets bigger because the mass of the Earth is significantly bigger. And what we discovered was if we keep trading in people, then the mass of the Earth and the radius of the Earth and the universal gravitational constant doesn't change. And so we end up calling that little g, which at or near the surface of the Earth is really 9.81 meters per second squared. So little g is known as the gravitational field strength. Okay, little g is the gravitational field. And so it's equal to gm over r squared, or it's equal to Fg divided by little g, if I just rearrange this guy. So this is called the gravitational field. Okay, strength. Whoops, I just can't get my arm in there to write it. There we go. Gravitational field. Strength. Okay, now gravitational field is the area around, like let's say the Earth, the area around the Earth where another object, you or I, would feel a pull due to the Earth. So we know we feel it on the surface. We put a little jetpack on our back and we go zooming up into the air. The further we get away from the Earth, the weaker this pull would be, but it would still be there. So when we talk about a gravitational field, it's the area around an object where another object, if it enters that area, is going to experience a force. Okay, so that's gravitational field and force of gravity. But now I want to talk about electrostatic. And exactly the same thing is true for particles that have charges. They're going to experience a force on each other too. It's going to be equal to kq1 q2 over r squared, which should look an awful lot like gm1 m2 over r squared. Q is the charge of an object. I don't know why it's Q, but it is, okay? So that means Q1 and Q2 are the two charges that the object has, just like up top, M1 and M2 were the masses. R is still center of one to center of the other. K, just like G was on top, K is a constant. And so you get FQ, an electrostatic force of attraction as opposed to a gravitational force of attraction. FQ is an electrostatic force of attraction or repulsion. It could be either one, because you know that opposites are going to repel and opposites are going to attract and likes are going to repel. Okay? So FQ, unlike FG, it could be a force of attraction or repulsion, whereas FG is always, always, always a force of attraction. You never have to wonder about, is the Earth going to pull you down or push you away? It always pulls you down. There's a couple of things in life you can count on. FG being a force of attraction is one of them. Me giving you homework is another one. Okay, so FQ is force of attraction or repulsion. How can you tell which? Well, it depends upon the nature of the charge. Nature. Are they positive or are they negative? Or are they one of each? Okay? If they're both positive, both Q's positive, then it's going to be a force of repulsion. And that is going to be a positive charge, a positive force, right? Because if both go in positive. If both Q's are negative, then again, you're going to end up with a force of repulsion, because like charges don't like each other. And mathematically, you're going to end up with a positive force. Two negatives multiplied together will give you a positive. If one is positive, one Q positive and one Q negative, then you're going to end up with a force of attraction. And that's going to be a negative force. And some people think a force of attraction shouldn't be negative. They think that's backwards. And so what I always tell them, so everybody who had me last semester knows this, that a force of attraction is negative, and it's set up for me. Because if you're a nun, then the force of attraction is a negative thing. Okay? And so negative means attraction. K, constant, is really 9. Well, I guess in Science 12.2 we use 8.988, I think it is, times 10 to the 9th Newton meters squared per coulomb squared. Charge is measured in coulombs. Unit of charge is coulombs. In physics, we round this to 9 to the 9th, and we don't use it very often in Science 12.2, and it is in the back of your physics textbook if you need it. Okay, so that's the electrostatic force. Now, how do we get electric field? Exactly the same way as we got gravitational field. To get gravitational field, whoops, I wrote a G there, and no one even corrected me. It should be an M when you rearrange. So we're going to get electric field exactly the same way as we got a gravitational field here. You're going to divide the electrostatic force by a mass. But this time we're going to divide the electrostatic force by a charge. You divide it by a mass to get the gravitational field. You divide it by a charge to get the electric field. The letter for electric field is a capital E. If you divide KQQ over R squared by Q, then a second equation for electric field would be KQ over R squared. So these are our two equations for electric fields. They parallel exactly our two equations for gravitational fields. This M is the mass brought into the field. The one on the bottom. Whereas this M is the mass